Hello students. In our previous video we defined electric flux. We also studied the properties of electric flux and subsequently we studied a law, that is Gauss law. As Coulomb's law was applicable on discrete charges, we need to have a law which could be applied on continuous charge distributions. That was the need of Gauss law. And Gauss law stated that electric flux through any closed surface is 1 upon epsilon naught times the charge enclosed by that closed surface. Here we have applications of Gauss law, that how Gauss law was helpful in determining the electric field due to continuous charge distributions. Our first application is a infinitely long charged wire. We need to determine the electric field due to this infinitely long uniformly charged wire. Here we have taken a charged wire with positive charge on it. Now we need to find the field associated with this wire. For that, as Gauss suggested, we need a Gaussian surface, that is an hypothetical surface, at every point of which the field remains same. So this whole surface, this is a cylindrical Gaussian surface, and this whole cylindrical Gaussian surface is divided into three parts. One is S1, the other is S2 and the third is S3. These two are cross-sectional views of the cylinder, that is S2 and S3, whereas S1 is the curved surface. Now to determine the electric flux, we first write the definition of electric flux, that is defined as dot product of electric field and area vector. Our whole, this A is the area of this cylinder. Now we have divided this area into three surfaces, that is S1, S2 and S3. So this equation is now bifurcated for three surfaces. So we have E dot ds1 for first surface, E dot ds2 for second surface and E dot ds3 for third surface. Now here we have taken ds1. ds1 is a small part of this whole curved surface, that is this part ds1. Similarly we have taken this as ds2 and here we have taken ds3. When we will integrate over this area, we would get the area of this whole cross-sectional surface. Similarly, if you integrate this ds3, you would get the area of this whole surface. And if we integrate this ds1, we would get the curved surface area of the cylinder. Here we see that this is dot product of electric field and our area vector. So by definition of dot product, we write E dot ds1 as magnitude of E into magnitude of ds1, and then we write the angle between E and ds1. So here if we see, the field lines will be outwards because this is positively charged, and the area vector, which is a normal on the surface, will be along the field line. So the angle between E and ds1 clearly is 0 degrees. So here we have E ds1 cos 0. Similarly, for these two surfaces, the field is outward, but area vector is a outward normal vector. So here if we see, the angle between E and ds2 is 90 degrees. Similarly, the angle between E and ds3 is 90 degrees. Thus, these two terms, they come as 0. So we are left out with E ds1. Cos 0 of course is 1. Now E is uniform, so E is out of integration and we are left with integration of ds1. So here, as I told you, this is curved surface of the cylinder. So if you add all these small ds1 areas, you would get the curved surface area of the cylinder. Okay, so this curved surface area of the cylinder is 2 pi rl, where r is the radius of the cylinder and l is the length of the cylinder. That is our Gaussian surface. Let us denote this as equation 1. Now, if we see, this Gaussian surface has enclosed the charge, that is Q, which can be written as lambda L, where lambda is the linear charge density, which we have already defined in our previous videos. So now we can write by Gauss theorem that phi is defined as q upon epsilon naught, and q can be written as lambda L upon epsilon naught. Equating these two equations, because left hand side is same, so equating their right hand sides, we get E into 2 pi RL is equals to lambda L upon epsilon naught. This L will get cancelled out and 2 pi R will come in the denominator. So E will be lambda upon 2 pi epsilon naught R. So here we see that the electric field is inversely proportional to the distance. Actually this radius is the distance from the uniformly charged wire, distance of our point of observation. So here E is inversely proportional to the distance, because lambda, 2 pi, epsilon, they are all constant quantities. So we can write this as E proportional to 1 by R. If we draw a graph between this E and R, our graph would be of this shape because of inverse proportionality. Likewise, as we had a uniformly charged wire, we have another continuous charge distribution, that is a uniformly charged plane sheet. That will be another application of Gauss law. So here we have a uniformly charged plane sheet and we need to determine the electric field of this uniformly charged plane sheet. This is also of infinite dimensions. We have taken it as infinite dimensions. Now again, for this we have another Gaussian surface which is also a cylinder, and as per the property of the Gaussian surface, the field at all points of the Gaussian surface has to be uniform, obviously. Now here again this cylinder has three parts. The two are cross-sectional views and one is the curved surface. But here the interesting point is that the electric field outwards at these two points, and here also the electric field is outward, that is on the curved surface. But the area vector for this curved surface is outwards normally. So for this curved surface, the field and area vector are making an angle of 90 degrees with each other. So there you will get EA cos 90. So this term would become 0 now. So we are left out with this curved surface, circular area, and here also we are having a circular area. So now the total field due to this plane sheet, it will be the total flux rather due to this plane sheet would be the flux through this surface and plus the flux through this surface, because the flux through this curved surface would come as 0. So now the total flux as per the definition of electric flux is again E dot A, and this total area of the Gaussian surface is now EA plus EA, because here the angle between area vector and field, it is coming as 0. We would here also make an area vector, that is our A, which is normally outwards, and here also we have an area vector normally outwards. So at these two surfaces, the angle between field and area vector, that is coming as 0. So here you would have EA cos 0 and here also you have EA cos 0, whereas for this you will have EA cos 90. So this flux through the curved surface would become 0. So now EA plus EA is the electric flux associated with this area and this area, which is same, that is A for both the surfaces. So we add this EA plus EA, we get 2EA. Let this be equation 1. Now the charge enclosed by the Gaussian surface, since this is a sheet, for this sheet we would have a term known as surface charge density, which we have defined in our earlier lectures. So the charge enclosed by this Gaussian surface here would be Q is equals to sigma times A, where A is the area, sigma is the surface charge density. Now we know Gauss theorem, that is electric flux is 1 upon epsilon times the charge enclosed by this surface, and the charge enclosed is sigma A. So we write phi equals to sigma A upon epsilon naught. From 1 and 2 we see the left hand side is same, so equating the right hand sides, we have 2EA is equals to sigma A upon epsilon naught. and we bring down this 2 and a down, so a gets cancelled out, so E is equals to sigma upon 2 epsilon naught. Now here we are not getting this R, whereas in this we got R. So here this R is missing, that means the field due to a uniformly charged infinitely long plane sheet is independent of the distance from the sheet. So if we draw a graph E versus R for a plane sheet, then you would get a line parallel to the x-axis, which shows that E is independent of R. In our next video, we would see the third application of Gauss law. Thank you. That's all for now.